Okay, so right now we're going to draw the secant lines for our position versus time graph. Now that secant is going to be a line that connects 2 points on our curve, and we're going to use those secants as an approximation of our velocities. So what I have here is going to be my position versus time graph from the ramp lab. You might notice that very faintly there is a curve drawn, but I didn't actually draw super dark because I want us to focus on the secants. What I'm going to do is I'm going to use a straight edge and do a point-to-point line. I'm going to do that for all of these points. So I'm going to click on my first point and then draw a straight line to my next point. I'm going to do that for each of these points. Straight lines for point-to-point measurements. We might notice that it's a bit harder to show that the slope is changing as our time increases. But it is very abundant, particularly for the first 16 seconds or so. Once I have drawn all of those secants, I'm going to label them. This first secant right here is going to be the first velocity that I know, so I'm going to label that as V0. Then the next one, V1, V2, V3, 4, 5, 6, 7, and 8. So ultimately that's going to be 9 different velocities that we have to correspond with those 9 change in positions that we have. In order to determine the velocity of any of these regions, we just need to use that same equation we know to determine velocity. Change in position over change in time. So I'm going to actually do that for velocity 1. So in order to calculate a velocity, it's going to be our change in position over our change in time. My position at the end of the secant for the velocity 1 region is a position of 0.20 meters, and I start off that region with a position of 0.10 meters. The time at the position of 0.20 meters is 8.38 seconds, and this is using my data. You will definitely have slightly different values here. My time at a position of 0.1 meters was 3.94 seconds. So my change in position, I would have gained 0.10 meters of position, and that would have occurred over a time interval of 8.38 minus 3.94 seconds. So that's 4.44 seconds as my change in time. And then when I plug that into a calculator, 0.1 meters over 4.44 seconds, I get my average velocity in this region. And that will be 0.023 meters over 1 second. That is not the velocity for every single time between 3.94 seconds and 8.38 seconds, but it is the average time within that time interval. Now that's actually going to kind of correspond with the time that is exactly halfway in between. So I'm also going to calculate my middle time in that region. So T mid. The way that we're going to calculate is that we're going to take the starting and ending times and add them together. So my 3.94 seconds is the time that would have started in this region. And I'm adding that to my 8.38 seconds where I ended up. And then I'm just going to divide that by 2. So my middle time there is 6.16 seconds. So at a time of 6.16 seconds, I can say that the velocity is most likely 0.023 meters per second, because that's what ultimately I ended up determining using our middle time and our average velocity using our secant lines. We can do the same thing for each of the other regions of the graph, figuring out the average velocity, V0, V2, 3, 4, 5, 6, 7, and 8, and then figuring out the middle times just by taking the average time in that region.